Hello, good evening everyone. So today we are having our 10th live session of this ultrafast laser spectroscopy course taken by Professor Anindya Datta from IIT Bombay, and I am Shruti. As you all know, I am one of the PMRF TAs of the course, and today we will be discussing our assignment number 9th one. So we'll start our discussion within few minutes. Let's wait for some people to join if they are joining. So let's start the talk discussion now. We are approaching the end of the course, and we have discussed so much of instrumentation in this ultrafast spectroscopy regime. So let's see now some excited state processes which happen. And let's discuss the first question first. So the first question is: excited state processes are often accompanied by redshifted fluorescence spectra, good overlap of absorption and fluorescence spectra, faster decay in red end of emission spectra, and rise time in blue end of emission spectra. So now when the excited state phenomena happens, so how do we know, how do we get a signature that something is happening in the excited state? So generally what happens that, so this is Kasha's rule that we have talked about Kasha's rule in the first or the second session, that the fluorescence spectra and the absorption spectra are generally mirror images. They should be. Okay, but for if something is happening in the excited state, for example, the proton transfer or some photoisomerization or something related to the excited state, then at that time there may not be the true mirror images of each other. So, and why these phenomena happen, what is the driving force? So the driving force for excited state processes is the change in the electronic configuration. So if I'll name some processes, it is excited state, proton transfer, it may be intermolecular or it may be intramolecular, photoacidity, photoisomerization, twisting in the excited state, and all these happens in the from the excited state. So how we will get to know that these any of these things are happening? So what is the all ended? change some settings. Yes, so the signature of the excited state process will be a redshifted spectra, redshifted peak. Suppose this is your normalized fluorescence intensity here, and here is your wavelength in nanometer. Then if this is the spectra when there is no excited state process happening, then if something happens in the excited state, then we can have something like this. So oops, it went something, we will get two peaks. So this peak will be from the mirror image of absorption, and this peak, this new peak, which is not there in the absorption but it comes in the emission, is of the nascent state or the new state where from to where the excited state process happen. So this nascent state is the state which is formed as a result of excited state reaction or excited state process. So it is at the red shifted region. So this one is lambda 1, this one is lambda 2. So lambda 2 is red shifted with respect to emission from the locally excited state. Okay, so if this is the ground state, this is the local, this is ground state, this is locally excited state, and here is some nascent state. So this is absorption, and when the emission, the this one lambda 1 is when it comes back like this is lambda 1, higher energy, so lesser wavelength. But when some excited state process happen, the molecule is in this state and it goes here and then comes down here. So this one is lambda 2. As this energy gap is lesser, so that's why this lambda 2 peak, this peak from the nascent state is redshifted. Okay, so answer to this question will be that the excited state processes are often accompanied by redshifted fluorescence spectra. Now let's discuss a bit about the rise time in the different red and the blue end of the spectra. So this nascent state was not there initially, so it is formed as the excited state process is happening. First it is formed and then the decay from this state happens. So on excitation, this state is populated initially over time and then depletes. Okay. Also, so this peak, this peak when it depletes, it populates this state and then depletes itself. And this one, it gets populated and then it also gets depleted. So when we will get when we will collect a decay at this wavelength, this one is decaying faster and this will decay slower, and it will have a rise time also because first this one is getting populated and this one will have a very smaller rise time but faster decay. So FL decay at high energy side, that is the blue end, Okay, so as I told, I have written that this is the locally excited state, this is ground state, and this one is the nascent state. So this is excitation. Now, when here we have some population, now this population has two pathways to deplete. So it can go directly to this ground state, or it can go to nascent state, and then from nascent state it will come over here. So it has two deactivation channel, whereas this one, this emission, it has only one deactivation channel. So the decay of this one will be slower than the decay of this state. So this state is the state of blue end. This is blue end because it has larger energy, and this one is the red end. Okay, so when the decay will be calculated at this wavelength, it will have a slower decay than this one. So how? It's right over here. The nascent state which gives the redshifted emission so this is the same thing, that the nascent state, first it gets populated because of the depopulation of the locally excited state, and once it has got enough population, then it decays. So generally our decay at these two wavelengths should look like this. Here we have counts. So the y-axis is counts, and here we have time. Okay, so for the blue end we will have a sharp decay like this, and for the red end it will first get populated and then it will decay. So this rise time is the rise in the population which is happening due to the deactivation of the locally excited state. Okay, so the question it was asking that we are getting rise time in the blue end of the spectra. We are not getting rise time in the blue end. The rise time is there in the red end. So this one is the rise time. Rise time in red end, and this one shows faster decay at, this one is the faster decay at the blue end. So this option is wrong because we are not getting rise time in the blue end. Rise time is there in the red end. Okay. And the option C is faster decay in the red end. No, there is no faster decay. There is a rise time in the red end and then it decays, and that decay is also even slower than the blue end decay. Good overlap of absorption and fluorescence spectra. This may not be the case for all the molecules. It may be sometime true, but not every time. And there will be some redshifted peak if excited state process is happening. So these two are also wrong. Hence, the correct answer is the first option itself, that excited state process are accompanied by the redshifted fluorescence spectra. Okay, let's move to the next question. Next question is the value of the time constant for fastest possible reaction at 400 Kelvin according to Eyring equation is. So this question we have discussed half portion of this question. So how we calculate the rate constant is the rate constant K is given by this equation comes from the activated complex theory. This we have discussed in previous sessions also, and this one is called the Eyring equation, which is mentioned here. Okay, now so for getting the highest possible reaction, the rate constant should be the highest. Okay, for K should be the highest. These terms should go to 1. So this is a fraction. The maximum value for a fraction is 1, and this is exponential, negative exponential. So for this also we can have when the activation energy is 0, there is no barrier in the potential energy surface, then the rate will be highest. So when activation energy is 0, this term becomes 1. Okay, so K, the rate constant, becomes maximum at, and it is given by kBT by H. Now at 400 Kelvin, we can put this temperature over here. K is the Boltzmann constant, 1.38 to 10 to the power minus 23 joule per Kelvin into 400 Kelvin divided by the Planck's constant, 6.626 into 10 to the power minus 34 joule second. Now on doing this calculation, it comes 83.3 into 10 to the power minus 23 plus 34 when this goes up. So this one is 83.3 into 10 to the power 11. Rate constant is 8.33. I have written it in scientific notation, 10 to the power 12 per second. Now here it was 10 to the power 11. I have shifted this decimal here, so it is 10 to the power 12 per second. Now in the question we have not asked the rate constant, we have been asked the time constant. Okay, so now time constant is the inverse of rate constant, because you can see it is per second, so we need time constant, it will be inverse. One over k. So it is 1 over 8.33 to 10 to the power 12 seconds. The second will go up, second inverse will go up and it will be second. Now this comes as 0.120 to 10 to the power minus 12 second, and when I shift the decimal it is 120 into 10 to the power minus 15 seconds, or 10 to the power minus 15 second is considered as 1 femtosecond, so it is 120 femtoseconds. So it is 120 femtosecond. The time taken by the fastest possible reaction at 400 Kelvin will be 120 femtoseconds. So answer to this question will be 120 femtoseconds. So it was a straightforward question, and I'll give you an exercise that do this calculation at room temperature, which is 300 Kelvin, and double of it at 600 Kelvin and 1000 Kelvin, and at lower temperature maybe at liquid nitrogen temperature, which is 77 Kelvin, and check yourself that how the time constant, that is the time taken by the fastest possible reaction to happen, what is the time taken. Now what is the fastest possible reaction? Now the fastest possible reaction in chemistry is basically just the bond breaking. Now this much time is taken by a bond to break at 400 Kelvin. So this is the fastest possible reaction. Okay, so this is 120 attosecond. What is attosecond? Atto is to the power minus 18 seconds. So we have not gone to attoseconds yet. We are in ultrafast regime where it is femtoseconds. You can quickly do these calculations and then check yourself how this reaction is temperature dependent, and obviously it is based on the activation energy, because we are taking the activation energy here to be 0. If it is not 0, the reaction will be even slower and it will take more time. Now moving on to the next question. Now, the next question is about the Ahmed Jovel's experiments. Now, the experiments which he did, the bond breaking, the experiments in which Joel did, the bond breaking time and the period of oscillation between bond dissociated and bonded states are respectively 1 femtosecond, 205 picosecond, or 1 picosecond, 205 femtoseconds, or 205 femtoseconds, 1 picosecond, or 205 picoseconds, 1 femtoseconds. So let's look back the experiments. Now this one, the experiment which he did is the photo dissociation of ICN. So why this ICN molecule? He could have chosen any other molecule which is familiar to us, but this is some strange molecule ICN. We never work around ICN. So it was chosen because its first electronic state its first electronic state has a minimum, and first excited state is dissociative. So it was easier for them to carry out the experiment. So you can see here, this is the ground state, that is the first electronic state, which is bonded. It has a minima, and the first excited state is not bounded or unbounded state. It doesn't has a minima, it just goes like this. So this state is dissociative, and this state has a is a bound state. Now, at that time, before doing this experiment, they knew that beforehand that when you excite the ground state with a 306 nanometer pump, you go to the dissociated state. So, ground state 306 nanometer gives dissociated state, and that dissociated state is I plus Cn. So here bound was ICN, ICN bonded, and I should not give this covalent, it's ionic, then it is I plus different atoms, I and Cn separated, dissociated state. So you can see here, this one, when it goes from here to here, this state is I plus Cn. So this is chi squared sigma plus state. And when you give a pump probe light, it's written probe here, but this probe light is actually exciting the excited state. So it is not just the probe, it is pump itself. It's not a pump probe experiment. Generally in the pump probe experiment, the probe doesn't excite or will have very less energy. But here the probe is energetic and is exciting this dissociated form, and it is giving Cn plus or excited Cn star. This one is Cn star. Probe is acting like a pump and exciting the dissociated CN fragments. Okay, so this is not a pump probe, this is two pumps one at a time. Okay, then what happens? What what they did in the experiment, they first the first pump light populates the chi-square sigma plus state, that is the first pump light, it produces I and CN fragments separately. So the bond between them breaks. That is the dissociated state. There is no bonding at this state. Then so there is no probe, it is just a second pump. The probe actually the probe at 388 nanometer now this probe light or the pump at 388 nanometer, it excites the field fragments, the cyanide transition of CN to CN star, and then there is corresponding emission from the CN star fragment. So for CN star, it is first getting formed from the CN. So for first of all, the ICN has to break. It has to generate some CN fragments, and then the CN fragment is getting excited to form CN star. And after that, the CN star is giving emission. So these many number of steps are involved, and this thing was studied by laser induced fluorescence. So there was no transient absorption at that time, so they did it with laser induced fluorescence. Now what was the result out of it was So the result which they got was like this. Okay, so at this point, the bond broke and there is increase. And then it became constant. So here, let me explain this. The fluorescence is not observed immediately because, as I told, for CN star to fluoresce, there are first beforehand the steps are that ICN has to dissociate, then CN has to get excited to CN star, and then it will fluoresce. So it takes some time to break. It takes for this ICN bond to break. And only after that the emission from the CN star is observed. So in this graph we had a rise. Okay, so the photodissociation happens within 600 femtoseconds, and the respective time period will be around will be around 205 plus minus 30 femtoseconds. Okay, so in the last question we here here we have actually calculated the time constant of the fastest possible reaction, which is the bond breaking, to be 120 femtoseconds. And now in from this experiment they got it at 205 femtoseconds, which was pretty good match because and this one that question was at 400 Kelvin, 100 Kelvin more than the room temperature, and these experiments were at room temperature or lesser than that. So it's fine that it is taking 205 femtoseconds and not exactly matching. Okay, so for this question, now the bond breaking time, so the first part we have answered that the bond breaking time, this one is 205 femtoseconds. So the options could be this or this. Now the period of oscillation is 1 picosecond per femtosecond. So let's see. In the next experiment, So in this experiment, this is also kind of same for dissociation. Here it is NAI bounded, and here is the dissociated form, this one. So what happens when they, so the emission is happening from this species Na plus. Now that emission has some wiggles like this. Free Na, this is the absorption, this is NaI absorption, and that time it was difficult for them to consider whether it is noise or it is the data itself. So they have finally came to the conclusion that it is not a noise and it is a data. Now when in transient absorption, so and so as the NaI is getting decomposed and is getting dissociated, there will be a decay for the NaI absorption, and there will be and since sodium is getting formed Na plus I, there will be a rise time for Na absorption. So this is what they got from the transient absorption. And these oscillations are not noise. So what happens when they are getting dissociated? It is acting like a oscillator, and the atoms are coming together, going apart, then coming together, going apart, and then finally it dissociates. So it oscillates between associated and dissociated form, and then uh, like a damped oscillator, it finally dissociates, and that's why there is a wiggle, these small peaks. So that's why these oscillations are not due to the noise, these are actually the data. So what happens and why this happens is because since excitation is being done by ultrafast pulses, and we have seen in earlier sessions and in lecture classes that ultrafast pulses are not monochromatic. It's not like when we are saying we are exciting by 405, we are actually exciting exactly by 405. We will end up exciting many more, not electronic levels but vibrational levels also. So these waves are getting formed due to there will be many wave. It will form a wave packet. So all those vibrational levels will form a packet, and these oscillations have been explained by the wave packet dynamics. Coherent wave packet dynamics. the wave packets the undissociated, the bound surface, or the dissociated surface. Okay, as I told, first it's dissociating, then it's coming back together, then dissociating, and then like a damped oscillation, it finally dissociates. And this oscillation period, so as you can see, this oscillation is happening within picosecond. So this oscillation period is 1 picosecond. So it is not femtosecond, it is picosecond. So to answer this question, we have finally, so it is not femtosecond, it happens in picosecond. So the answer will be the C option. Okay, let's move to the fourth question, which is regarding the mechanism of acid-base reaction proved by pump probe spectroscopy. The higher concentration of the solvent molecules leads to no change in the rate of reaction, increase in the rate of the reaction, decrease in rate of reaction, or first increase and then decrease in the rate of reaction. So the acid-base mechanism, it was which we discussed in the course was this one. So we had pyranine molecule so this was the photoacid, and then I should write straight, and then we had the base, so the minus charge is shown as a resonance structure, which gave now instead of H we have taken D, deuterium. Now deuterium, because it was easier to see signals with deuterium. Now this one is the photoacid, pyranine, and here is the Here is its photo base, and this one is deuterated acetic acid, and here it's a regular base. Acetate ion is the regular base. Okay, so this was the reaction which was discussed, and it was done by Neighboring's group. Okay, and the mechanism which they gave, so the acid-base mechanism which they concluded, at low concentration. So first let's discuss at high concentration. Mechanism 1, at high concentration of acetate, which is, I'll refer to it as B minus, this one is ROD, this one is RO minus, and this one is deuterated D base. Okay, so at high concentration of acetate, that is B minus, so high concentration of this means, or low concentration of solvent. Now what happens here is we have ROD, and since there are so many acetate ion high concentration, there is a direct contact with a acetate. So they have contact ion pairs. Okay, so when this D plus is released, it is directly accepted by B minus. B minus, and immediately RO minus and DB is formed. Okay, so this one and RO minus and this one are getting formed at the same time, so that's why they have the same kind of dynamics. So when D plus is released, so there is no barrier, nothing in between, and we have large concentration of acetate ion. So when the acid releases the proton, it is immediately accepted by the acetate ion, and it forms RO minus and Db plus. So there is no time delay between the formation of RO minus and Db. So they have the same kind of dynamics. But in the second mechanism, So in the second mechanism, when there is low concentration of the acetate ions, or which is the same as the high concentration of the solvent, here the mechanism of proton transfer is little different. So here first we have this ROD plus B minus. So this forms here the solvent molecule comes in between, diffuses, and this is called the encounter stage. This is kind of encounter complex formed D2 because we are taking D2 B minus. So this is the encounter stage. After that, there is a reaction happening. The solvent molecule goes in and then the proton transfer happens. So this is the reaction stage. So in this mechanism, since when the proton is released, we get the photobase. When the proton is released, so what we get is RO minus is formed RO minus is formed immediately, but the acetic acid formation is slower. So why it is slower? Because we have so many solvent molecules in between. So it takes time for the proton to get liberated and then getting attached to it gets attached to the solvent molecule in between, and then it finds a acetate ion. So there is a time lag between the formation of the photobase, which is RO minus, and the formation of acetate ion. Because the liberated proton or the released proton gets attached to solvent molecule. So at higher concentrations, acetic acid formation is slower. So the proton transfer process is slower at the higher concentrations of solvent. Okay, so that's what was asked in the question, that regarding to the mechanism proved by the pump probe spectroscopy, the higher concentration of the solvent leads to the decrease in the rate of the proton transfer. So the answer will be decrease in the rate of the proton transfer, because the proton is getting attached to the solvent molecule and it takes longer time for them to find an acetate ion and form the acetic acid. So the whole proton transfer process gets delayed because of those solvent molecules. So thus the concentration of solvent molecules on increasing, it decreases the rate of the reaction. So this was shown by this decay profile also. So this is for the rise time of so the rise time of acetic acid will be faster, will be less when there are no solvent molecule, or there is more concentration of acetate ion. So as the concentration of acetate ion increases, the rise time decreases. Concentration of acetate ion or decrease solvent concentration. So that's what it is shown like. So if this is for a higher solvent, higher acetate ion concentration or low solvent concentration, and this will be for high solvent concentration, this is low solvent concentration. So let me write the excesses. It is signal or intensity, and here is the time delay in the picoseconds. Okay, so this was the answer for this question. It was the mechanism of the acid-base reaction or the proton transfer. Let's move to the next one. So this question is related to the twisted intramolecular charge transfer complexes. One of the complexes given, that dimethyl aminobenzonitrile DMABN. Dual emission is observed in all solvents. The maximum of the Stokes shifted emission band is polarity dependent. The position of the maximum of the locally excited band is polarity dependent. The height of the energy barrier of the excited state is viscosity dependent. So here I have given the picture of the emission, and which has been taken in different solvents. So I don't think it is visible. This one is for hexane. The second one is for dibutyl ether. write here. 3 is for, this one is the 3. 3 is for diethyl ether. 4, this one is the fourth one. It's coming like this. Fourth one is for butyl chloride. And the fifth one is here. The fifth one is acetonitrile. Now, dual emission is observed in all solvents. This one is wrong because you can see there is dual emission here in the fourth one, which is butyl chloride, but in 1, 2, 3 and 5 there is only one emission. Whatever be the wavelength, whether redshifted or blue shifted, there is only one peak. Only in the case of butyl chloride, the fourth one, there is dual emission. So this statement is wrong. The next one is the maximum of the Stokes shifted band is polarity dependent. Now Stokes shifted band maxima. Stokes shifted band is this one, which is the red shifted band. Here this one is in wave number inverse, centimeter inverse. So this end is the high energy end. This is high energy end, and this is 16 centimeter inverse. 16 centimeters. So this one is the low energy end. So low energy end. So this one is the red shifted band, the fifth one. And fifth one is red shifted in which solvent? In acetonitrile. And among these five solvent, this one is the most polar. So it is true that the maxima of the locally excited band is polarity dependent. It is coming from the most polar solvent. So the maxima of the Stokes shifted emission is polarity dependent, which is true because all are non-polar and this acetonitrile polar, and it is coming at Stokes shifted. So B option is true. The position of maxima of locally excited band is polarity dependent. So this one is the locally excited band. This is the high energy end. This is the blue end. This is the blue end. And this is the red end. So this one is the locally excited band. This part. So is this the maxima is polarity dependent? The maxima is more or less same. Except for this, the maxima is more or less same. So we cannot say that it is highly polarity dependent. So this option goes wrong, that the maxima of the locally excited state is not polarity dependent. This one is wrong. And the fourth option is the height of the energy barrier of the excited state is viscosity dependent. So there was one more experiment done in this regard, the viscosity dependence. and the polarity and viscosity dependence, and it was plotted. This is the and here it was the polarity parameter, which is ET30 value. And for isoviscous, there was one plot, and this is isoviscous. Polar aprotic isoviscous with CN octane. So in this mixture, octane it's non-polar, and this solvent it is polar, but it is aprotic. But both have same viscosity, isoviscous. And in this one, this is also isoviscous. One alcohol and hexadecane. So this one is polar protic, and this one is non-polar. And this one is the y-axis is the ln K versus ET30. ET30 is the polarity parameter. So now the twisting motion shows viscosity dependence highly. The twisting motion shows viscosity dependence because if the solvent is more viscous, it will take more activation energy for the molecule to rotate or for it to twist. So that's why it shows a viscosity dependence. And the polarity dependence is in terms of the charge separation. So if it is more polar solvent, the charge separation and solvation will be more, and there will be a large dipole moment. So the height of the energy barrier of the excited state is viscosity dependent. This statement is true because if it is less viscous, the energy barrier for twisting will be less. So this statement is also true. Okay, let's move to the next question. For dimethyl aminobenzonitrile, the same molecule DMABN, the charge transfer band is readily observed in. So in this same figure itself, this one is the charge transfer band. So this one is the charge transfer band, fifth one, because it is redshifted. And as we have discussed in the first question, that excited state process has a signature that it happening has a signature that it will give redshifted peak. So this one is redshifted, so this one is showing charge transfer band. Now in which solvent it is prominent? It is prominent in the fifth one, which is this acetonitrile. So the answer to this question is straightforward, that the charge transfer band is readily observed in acetonitrile. Due to more polarity, there is large dipole moment. And hence there is a charge, there is a charge transfer can happen easily. So that's why it is observed in acetonitrile. Let's quickly move on to the other questions. We have a lot of questions left. So the seventh question is about ET30. What is this parameter? So this ET30 is the empirical parameter. It is empirical micropolarity parameter, and it was set by with reference to the absorption maxima of betaine dye. Unit is kilocalorie per mole. So yeah, the answer to this question, it's not viscosity parameter, it is polarity parameter, and it is derived from the absorption, not the emission. Absorption of the betaine dye. So for this, A and D is the correct option. And here I have kept some solvents and their ET30 value. And since it is polarity dependent, a solvent which is more polar or highly polar uh, will have more ET30 value. So suppose we see here methanol, it has a value of 55.4, whereas this toluene is less polar, it has only 33 values. So it's a polarity scale kind of, we can say that uh, it classifies the solvents according to their polarity scale. Acetonitrile comes somewhere here, 45.6. So the next question, it's asking the difference between the activation energies of alcohols and nitrile is equal to energy of CN bond, CH bond, H bond, CC bond. Now here we are checking the activation energy, which means the temperature, the effect of temperature and H bonding. So effect of temperature and H bonding. So as the temperature increases, the polarity decreases. So at lower temperature, polarity is more. Why? Because there will be directionality. At higher temperature, it's the dipoles are very random rotating, so the polarity decreases. At lower temperature, polarity is more. at higher temperature, solvent dipole will rotate and it leads to the decrease in the polarity, or this ET30. So now it is asking between alcohols and nitriles. So which is more polar? Alcohol is more polar. So activation energy of this is some constant. This is ET30 value minus 30. So this 30 is not same as this 30. They are not related. So because ET30 value of alcohol, it's more, this we are considering the solvents for charge transfer, and the difference is 6 kilocalorie per mole. Activation energy is and this 6 kilocalories per mole is the energy of a hydrogen bond. Okay, so that's why here in the question what we have been asked, that the difference in the activation energies of alcohol and nitriles is equal to the energy of a hydrogen bond. Okay, so that's how we answer this question. Let's quickly move on to the next one. So for molecules with uh, ground state and excited state with different dipole moments, the Stokes shift between absorption and emission is greater for less polar solvent, more polar solvent, molecules with greater excited state dipole, molecules with smaller excited state dipole. So there was a graph. There was a spectra showing different emission in different solvent. This is a normalized FL intensity, and here is the wave number. So it's reverse of frequency. Sorry, reverse of wavelength. Okay. So for this one, if this one is for acetonitrile, I'll use different colors. This one is ethylene glycol, EG. Okay, then there was one spectrum. This is for ethanol, and one was for water. So the solvent which will have more polar solvent, it will have more stabilization of excited state dipole, and it will show greater Stokes shift. Considering that the excited state dipole moment is greater than the ground state. So molecules with greater excited state dipole, the Stokes shift will be more for more polar solvents. Okay, so answer to this question is, I think I have written reverse here. Maybe this is wavelength only. Frequency and new bound, the same thing. I think this is wavelength only. So that's why here water is a more polar solvent, then it can stabilize. The emission is more redshifted because this can stabilize the excited state more as compared to the ground state. So the More the stabilization, lesser is the energy gap between the ground state and the excited state, and hence lesser the energy gap, more is the Stokes shift. So that's how we answer this ninth question. Now this question is straightforward, that the solvent response function is given by nu t minus nu infinity divided by nu 0 minus nu infinity. So it's just these four combinations have been made by changing these nu t and infinity and nu 0 here and there. So for us, nu t minus nu infinity, this one, by nu 0 minus nu infinity. So this one is the correct answer. And this has been got from time dependent Stokes shift, TDSS. This correlation is nu t minus nu infinity divided by nu 0 minus nu infinity. We have 3 more questions left. Let's do this fast. Now the decay of CT in correlation in cyclodextrin is faster than water, is slower than water, is single exponential, or is multi-exponential. So here you can see I have kept the correlation decay. The dash ones for cyclodextrin, this one. So the water one seems faster, the cyclodextrin is slower. So it is slower than water. And does it seem to be single exponential? Not at all. I can, here it is 1, here it is 1. So it seems multi-exponential, or it can be tri-exponential also, 1, 2 and 3. So let's see. So it doesn't seem from like just by seeing at this dash line you can say that it is not single exponential. So it is multi-exponential, and it is slower than water, because water decay is faster. You can see it is getting complete faster than the cyclodextrin. It is slower than water. B and D. So the 12th question is, the solvation time inside CHO cell has been found to be in order of liquid droplet, then cytoplasm, then nucleus, or nucleus, then cytoplasm, then liquid droplet, or cytoplasm, nucleus, liquid droplet, or liquid droplet, nucleus, or cytoplasm. So here in the lecture it has been discussed the solvation dynamics of C153 in the live CHO cell, and we saw that there the nucleus had the time solvation time was for nucleus, it is 750 picosecond. For the cytoplasm it was 1100 picosecond, and for the lipid droplets it is 3600 picoseconds. Okay, so we can clearly see that lipid droplet has higher solvation time than the cytoplasm and then the nucleus. Okay, so to answer this question, this is the first one is the correct option. So you can see here the correlation for the lipid droplets. It is because its solvation time is too much, so the decay is slow. The nucleus, its solvation time is very fast, decays. Solvation time is very less, decay is fast, and cytoplasm is in between. Okay, so the answer of this question is the A, first option itself. Now the last question, in the vibrational spectra of the liquid water, depopulation of coupled B2 state of OH bending state occurs with T 800 femtosecond, causing delayed population of equals to 1 state of OH bending, which decays with T 270 femtoseconds. Or the depopulation of the coupled V equals to 2 state of OH bending occurs with T at 200 femtoseconds, causing delayed population of V equals to 1 state of the OH bending, which decays with 170 femtoseconds. Now slower kinetics of 1 picosecond after a few liberational period is attributed to the intermolecular energy transfer to the hydrogen bonded network, or the slower kinetics after a few liberation period is attributed to the intermolecular transfer from the hydrogen, either to the hydrogen bonded network or from the hydrogen bonded network. So it's a MSQ question. So here you can say that see from the vibrational spectrum of liquid, it has stretching mode, bending mode, and liberation modes. Liberation coming from the hydrogen bonding. So for this, the correct answers are B and C, which is that the depopulation of V equals to 2 state of the bending, V equals to 2 state of the bending occurs with 200 femtoseconds, causing delayed population V equals to 1, of which decays with 170 femtoseconds. It should be stretching here, I guess. So from here to here, this is 200 femtoseconds stretching, this is 170 femtoseconds bending, and the slower kinetics, it is attributed to intermolecular energy transfer in energy transfer to the liberation modes. So liberation modes are due to the hydrogen bonded network. so the coupling between all these three modes happen, and there is a redistribution in the vibrational energy, and these time scales are in ultrafast regime. So to answer this question, it is option B and C, as you can see from this diagram itself, that V equals to 2, tau is 200 femtoseconds of the stretching mode, and then it is coupled with V equals to 1 of the bending mode, which decays with 170 femtoseconds. And the slow kinetics is all due to there is a coupling between all these modes, and it is due to the hydrogen bonded network, which forms large amount of these energy levels called the liberation. Okay, so we have finished today's discussion, all the 13 question of this assignment, week 9. So we will be discussing the 11th and the 12th assignment together in the last week, because next week will cover the week 10 assignment complete, and then 2 assignments we'll have to do together in the last week itself. So I'll finish this session today. See you everyone next week.